Okay, yeah, it started recording now.
Okay. Yeah, so I'm not going to speak about any new papers or anything like that. This is probably more of a tutorial type thing. I hope that's okay. So I'm going to talk about Qubitisation and essentially how that leads to quantum signals processing and all these very advanced algorithms that come around. But I'm going to try and give some intuition behind the problem and like the how things were developed essentially. So all right. So yeah, block encoding is essential to this idea. Essentially how you get a matrix into a circuit, and then Qubitisation is really the first use case of doing something interesting with a block encoded matrix inside a circuit. And it's essentially the same as implementing the Chebyshev polynomials of a operator on a at the circuit level. And then I will show how this is the first useful use case of this is for Qubitised phase estimation. So there's a paper from 2018 by Ryan Babish and the Google guys called linear T-gate complexity for quantum phase estimation. That uses all of this Qubitisation combined with phase estimation, but it's very buried in the it's buried like what the kind of intuition is buried in that paper. So I will hopefully try and show you why they're doing some of that stuff, and then I'll show how you can then use QSP to then do kind of eigenvalue transformations on the matrices and things like that. Okay, so why do we want the block encoded matrix? So circuits are typically unitary. That's quite restrictive, but we can get around that by putting non-unitary matrices into a small subspace of that matrix. Typically, yeah, so this is what we call block encoding essentially. So we have to post-select, project ourselves into that matrix at the end of the circuit. But really how I think about these things is you're just getting a matrix into a circuit to try and do some cool stuff with it, basically. And then the result of this work, this talk will hopefully give you some understanding of how we can do functions, polynomial approximations of these functions on these circuits. And that's really what Qubitisation plus quantum signal processing leads to, is matrix function approximations in the quantum circuit. Now, I won't talk about any complexity or anything like that. I'm just going to talk about just trying to give you the intuition behind these problems. Okay, so the typical example, the main, yeah, you've probably seen some of this before, but I think it's important because it's very central to the topic. So linear combination of unitaries is probably the most natural way to block encode chemistry Hamiltonians. There are other ways, so you can take like there's some work recently with like sparse matrix block encoding. Things like that, we're just directly inputting the matrix. But the very natural way from taking quantized chemistry problems is LCU, because obviously you start with your second quantized Hamiltonian, then you can do a Jordan-Bingham transform, and you naturally already have a linear combination of unitaries. And then so you don't need to do anything extra, really. Yeah, we basically want to be able to put this what symbol is this?
Capital upside.
I don't know what I borrowed my colleague's slides for this. So I would not have chosen that either. So yeah, that's the operator we want to put in. It's in the operator representation. There's no basis yet, but yeah. So here's a quick example. So the toy model I actually uses this alpha x plus beta y, and then we use the constraints. We constrain the term weights to be alpha plus beta, so this should be alpha squared plus beta squared equals 1. That allows it to be normalized. When you'll see for a second. So essentially, this constraint means that we can encode the weights of the powers into an RY matrix really nicely. So if we're starting on there's always two registers in an LCU circuit. So you have what's called the prepare register and then the select register or the state register. And the prepare register acts on this RY matrix acts on this prepare register and it encodes the weights of the terms. So it's acting on the 0 state, therefore it acts on this column. So you can see 0 will be square root of alpha, the x term, square root of beta with this term. And you can see how this could generalize to larger systems. Like if you had 10 terms, you could use 4 qubits And it scales, the preparator scales logarithmically the number of times in your register. Okay, so yeah, so you can see that. So this is how we do it. So we encode this first step encodes the weightings of this acting on the first column. So you can see that. So then we want to selectively apply the operator terms to their corresponding coefficients. Okay. So we do that with this multi-controlled operation. Well, in this case, it's a single controlled operation, but so using the 0 controlled x, it selectively applies x to its coefficient, and then 1 controlled y, applies y to its coefficient. Now, we need to then rotate. To be able to get this information out of the circuit, we have to rotate back into the 0 state. So you can see this is before and this is after. So you get this other term here. Let me rotate back. And then measurement, basically, by orthogonality, you can just remove the overlaps, and you get this nice application of the information unit. Now, at this point in the circuit, it's very important to remember this is not a expectation value or a not expectation value. This is just equivalent to like a matrix vector product. So you've got the matrix acting on the vector state, and now that the matrix is inside the circuit essentially. So this is now we have to kind of think a bit beyond the typical LCD picture where they act on the state in this case. We have to start thinking about the entire unitary in the whole for qubitisation and things like that. So if we now don't post select, we just stop here. This is a larger unitary, and you can see what we've done here is this RY is this is the prepare register. I need a pointer. Yeah, so that RY is acting on the prepare register, and then the tensor point is I is acting on the state register.
I don't know.
I use this.
Yeah.
Yeah. Yeah, so this is acting on the it's still blank. It doesn't matter, it's fine. Well, I can use my mouse, so yeah. Yeah, so this I think you can go laser pointer. There we go. Yeah. So yeah, so this is acting this is in the operator representation. So this RY is acting on this register, and then this identity is acting on the state register. So you can see that here. It's like a box. And then we have the X. So this middle part, this horrible notation. This is a diagonal operator acting on X.
Oh, okay, that's where the brackets are.
Yeah,
Okay,
yeah.
yes, yeah.
And then again, we have the RY here. Now, I think this is a perfect example of where tensor point notation on one line is just completely insufficient to describe things. This is really, it's like diagrammatic tensor network notation is really much more natural to describe these things. And the circuit is one of those examples. So I just think in the circuit, I don't even bother with this stuff. It's kind of annoying that a lot of papers insist on. I wish there was a way to like generalize this just to drop these annoying ways of thinking about it. So yeah, now when we multiply this out, etc., you see that we get this because this is because this is 1 qubit, we get a 4x4 matrix when we're thinking about 2x2 when we're kind of projecting onto this space. Okay, so we've got the 0, 0, the 0, 1 to the top right, top bottom left, and you can see essentially the ones that we'll be concerned about will be the 0, 0 and then 1, 1, and you can see that the signs, the coefficients here basically flip. Yeah, because obviously it's just acting on the state here, and it's quite instructive in this case because this is a 2x2. You can see that these two vectors will be orthogonal. this is a reflection across the x-axis. Now this orthogonality idea is central to the Qubitisation approach. It's like, it's really gives you this intuition.
So if you were just using this as the LCU, you necessarily have to, if you wanted the 0,0 component, you lose a hell of a lot of amplitude.
Exactly,
Because
yeah.
the magnitude of it is the same as the 1,1.
Yeah, yeah.
So, yeah.
So yeah, so yes.
So you can use it instead. Is that right?
Yeah, so then, well, yes, so you never explicitly use, it's a very weird, so the orthogonal space takes part in the processing, but you always project into, you'll see in a second what I mean by this. You always measure, you have to measure in one basis, unfortunately, but while the computations happen, you can exploit this orthogonal space, and this is kind of you may have seen quantum processing expressed in kind of a sphere-like picture where you're iterating around a sphere. This is exactly what's happening. It's like you're exploiting this orthogonal space to like manipulate your operator. But anyway, okay, yeah, and then yeah, so else you would project. In the general case, we kind of represent it like this, where we have our 0 state, and then we have which is the register. The 0,0 register, the 0,0 state of the pair register, and it's blocked on every other bit of the pair register, and there's a psi basis inside each one of the blocks. Yes, but you can essentially think about it in exactly the same way, is that there will always be one state, 0,0, and then some orthogonal space, because you can do some sort of Gram-Schmidt type procedure or whatever. There'll always be an orthogonal space existing perpendicular to that 0,0 state, and that's really at the heart of Qubitisation. Yeah, okay, I'm not really interested in that. And I repeated the same slide. Okay, so this is what I mean. Oh yeah, and actually, yeah, so it's not obvious from this picture, but when you diagonalize this, you get the negative eigenvalues of the 1,1 space. I had tried to prove it yesterday why it is, but I couldn't do it basically. But the eigenvalues of this operator will always be negative of that one.
So they're related by a rotation, or
Yeah.
no, a minus reflection rotation.
Yeah, yeah,
That minus is the because the x and y version of those.
yeah.
Okay, probably. So
Yeah.
you have to reflect in order to get the same structure as well as the.
Yeah, I thought about kind of like you could similarity transform the whole operator. You might be able to get something a bit nicer, but yeah, I wanted to have that example, but I couldn't do it, unfortunately. Just have to take my word for it. Anyway, so this is what happened. So, yeah, so what I wanted to prove to you was what these stars were by that argument, but because but they're just other parts of the unitary. I mean, we show in this example what they are,
yeah.
But in the general case, it's not obvious, is what I'm trying to say. But what we see is that when you act on the eigenbasis of H, which is your operator, which was that epsilon. Okay, so we now, this is really important. So we block encoded H here, and then we don't know what the orthogonal, what the matrix is of the orthogonal spaces are in the rest of the matrix. But when we act on the eigenvector, where the eigenspace, when we act on the eigenbasis K, some eigenvector, we'll always get this relation just by a simple orthogonality argument.
Yeah.
Yeah. Yeah.
The projectors decomposes space.
Yeah, exactly.
Can there be a phase on the right hand side? On the right.
Yeah, so I'm just thinking about permission matrices at the
Okay.
moment. Yeah, so that's a good point. So I should say there are non-permission implementations of this, but they came after So I'm just going to talk about the traditional emission matrix. So thanks for reminding me. But yeah, so this is super essential. Is that when you're acting the eigenbasis of your operator, you end up with, you will always have this 2 by 2 two-dimensional space where you have the orthogonal space of the eigenvector here. And it's kind of intuitive in the one cube in the single cube. Let's just say one ancilla. I apologize. So in the one ancilla case, it's quite instructive because you can kind of visualize the orthogonality quite nicely. Because if you know that if the state register, this guy is in K and this guy is in 0, you can see quite nicely how this would.
Don't you require though that what you're blocking coding, unitary itself is Hermitian?
Yes, yeah.
For that relation there to be true, for your bottom, for that to be a reflection.
Yes, yeah. So I think for the when you have a Hermitian, when you block encode a Hermitian matrix,
Because you can apply it again. If it's not, then you just get this jumping between the two spaces.
So I think that's, you include a reflection to break that. I think that might be what you're referring to. Because any block encoding of a Hermitian matrix is going to be U squared equals I. So you can play it twice, you always end up with the same eigenvector.
Yeah, exactly.
Yeah. So yeah, but we do break that constraint with an extra operation in a second, so I'll get to that. But yeah, I think in the Hermitian case, when you have a Hermitian matrix, you will always have a Hermitian block encoding, I believe. And then as you're correct, then you always have this. The main idea is that you have this two-dimensional subspace, and this is really central to lots of ideas in quantum information. Is that you have this Qubitised space, right? This is what it means. You have this. You have some space, and then it's orthogonal complement, and that's very easy to visualize in the single qubit case. You just have 0 and 1, but you can also generalize it quite easily to larger spaces because there'll always be an orthogonal complement existing to the vector space. I'll come on to that in a second. Any questions so far? Because this is really the takeaway point, I would say, from this lecture. Okay. Now, obviously, if we have the full linear combination of eigenvectors, we can then use this very nice direct sum of all the eigenvector spaces. So how I like to think about this is qubitisation essentially takes each eigenvector space and then just splits it into the orthogonal and the orthogonal complement. Yeah, so this is what the unitary. This is basically what any ULCU breaks up into when you have when you act on the eigenvector basis. Okay. And this is only in the single qubit case, but it's general as well. And this is really at the center of everything. But yeah, so this is interesting, but can we do anything with it? And this is kind of where people started to apply these tricks to it and take it further. So I think this is kind of what you're saying, is that when you have a Hermitian matrix and it's unitary, you get this nice relation where U squared equals I, and obviously U to the power of.
So involution.
Yeah. Idempotencies. Yeah. But yeah, essentially, this obviously means we can't do much because obviously you'll apply it lots of times and just then end up back to the same place. But what you can do is you can apply a Z operator to the unitary, and we get this W matrix, which is known as the qubitisation iterate, and it's actually equivalent to a Grover iterate. This is one of the nice joining up factors that kind of unified a lot of things, is when they realized that. What this means is that by applying the Z to this single qubit subspace, we take this negative and apply it onto the off diagonal. And now this gives us more freedom. And as some of the observant among you might recognize this as a case, RY gate. It's just it's a rotation now. Okay. So this is really, now we can start to do things interesting in this Qubitised subspace of the eigenvector. And I used to struggle a lot with this when I was first learning about it, about like the eigenvector space, but you can always express and operate in terms of its eigenbasis. So this is really just completely general. So now we have a rotation because we've added the Z U. And yeah, so you can see now we have this, we can represent this as an RY, where we take our eigenvector, eigenvalue, and make it equal to cosine theta k. And the signs are related in the same way. And there's this clever, I don't know what you would call it, like a identity, I guess. When you have this symmetry matrix, you can represent its eigenvalues like this and its eigenvectors like this. Okay. Now, this is kind of where the first applications of this use case, where it's that you might notice that the eigenvalues are now contained in this slightly different object. I think there should be an I there.
There should be an
Yeah, sorry.
yes.
Sorry. Yeah. But just like in phase estimation, where you do e to the IH2, and you get the eigenphases are isospectral to the eigenvalues. I think that's what the penalty. We have the same thing, but now we just have a slightly different exponentiated unitary matrix. So you can still do powers of the unitary and get a relation back to the eigenvector value in exactly the same way as you would with phase estimation for the time evolved operator, Hamiltonian. Yeah. Okay. Anyways, so just going back a step. So when we apply these powers of the rotations, applying the rotation d times is just going to rotate you more and more and more each time. And so this basically, the case that just increases the angle in the rotation. But this basically has the form of the Chebyshev polynomials. So yeah, this is the. I like to think about it in this way because it's just like a double angle formula on steroids. But yeah, this I yeah. But yeah, so
is this the Chebyshev?
Yeah.
First thing.
So you can treat this as arc cos theta. Wait, arc cos lambda, I think, and that's where this. Yeah, that's how you get to this equation. I was going to have a slide on Chebyshev polynomials, but I ran out of time. I apologize. But yeah, so this is the point of this is what I'm trying to say is that we're doing a Chebyshev. So we've got the eigenspec. We're acting on the eigenbasis. We've formed this 2x2 Qubitised space on the eigenvectors. We apply that over the whole eigenspace with this direct sum, the orthogonality, and then now we have the first application of a matrix polynomial. And because that polynomial acts on the eigenvectors, the way that obviously matrix functions work in linear algebra is that you do SKD and then apply it on the singular values. This then obviously generalized. That means that we're applying this polynomial to the operator itself. So this is the first application of the matrix polynomial via a quantum computer, essentially. So this is really cool. It's not particularly useful. Like you need to start generalizing it and mangling it a bit, which I'll come on to later. But you can use Here's just an example. Yeah, you can use it for phase estimation, which we'll talk about in a sec. Yeah, so here's a simple taking that example from earlier. We can just form the Chebyshev polynomials of our operator just by applying this simple operator. So I don't think you see this in the literature, but it's one of these examples again where if you break it down to the simplest case, it becomes incredibly easy to implement. But lots of the papers are interested in the complexity and not really the implementation. But yeah, so take this one away with you, I guess. Yeah.
So it's sort of the key here, you're encoding basically Z back and forth with the rotation Y, and that's what's this complexity effectively. Because when you place these next to each other, you have a string of, you know, RY theta Z inverse RY. You keep on doing that, and you just
Yeah, back and forth. Yeah,
that's effectively producing this polynomial, which you're then encoding with the X and Y information in it.
Mhm.
So,
Yes, it's a fairly simple polynomial, so maybe it's nice, but it's maybe not so. Like, yeah, when you start to use different phases in between phase modulation,
yeah.
that's when you can start to get like higher variance and modulate your polynomial a little bit better.
The application is perhaps a bit unclear at this point, but it's a nice result, I think.
Yeah.
And keep it.
Very cool result, yeah.
It's built upon in the next slide. Okay. The main idea is that we can get this polynomial, Chebyshev polynomial of a operator. But we now need to do something with it. Oh yeah, in the general case, this is the general LCU example. This should be rescaled, but I've been nosing by the norm. And also, I think I don't like this slide. Yeah, so, yeah. This is actually wrong. I've realised. So if this should be an eigen basis, because this is what I was trying to derive, but it's not general. It is in certain cases, but in the LCU case, this is not true. So you can only show this should be k, and this should be lambda, and lambda. It's quite spooky, I think, that the matrices aren't the same, but then you get the same eigenvalues. So I guess unit rotations and
they present the eigenvalues.
yeah. So yeah, so the general case is exactly the same. So this is what I mean. So obviously there will always be an orthogonal space in your perpendicular to your 0,0 state on the prepare register, and you don't really care what it is. You just care that it exists because that generates this 2-qubit subspace. So the idea is exactly the same, even though it's quite difficult to comprehend. I actually much prefer. You'll see in a second, like what they exploit is that there's always an orthogonal space existing on this register, but you can be slightly more explicit and project onto a qubit, and the qubit always has this orthogonality, which I think is much easier to understand. You'll see in a sec what I mean. Yeah, sorry.
The name Qubitisation is sort of quite clear because of that, because you've just got these two, zeros and everything else.
Yeah.
That's effectively 0, 1 as a qubit. So it's always been a bit mysterious.
Yeah, but it's quite a simple idea, really. It just someone needs to explain it clearly.
Yeah, rather than the appendix of the the third kind.
I think also a fair point maybe to make is that it is fairly hard to actually get to the implementation and the details about what's going on here. If you go and read some of these seminal papers, it is very, I mean, deeply, and it's not entirely clear what is meant. There are updates, there are recent advances on it. So it's a challenge to actually figure out what these names mean and what the foundational idea is.
The authors often would have very different goals to what I think we would as scientific computing minded people. We want to do stuff with it, whereas then we're interested in the complexity and things like that. And so I think there's a lot of space for nice papers of implementations of these things. It's a bit frustrating because the community and the reviewers are quite focused on complexity, whereas I think they're beginning now to realise that we need the tools and need to actually start doing some heuristics with these things.
Do we need a new journal? The journal
Yeah.
quantum computing application.
Yeah, implementations,
Implementation, yeah.
constant compilation or something like that. Oh, yeah, maybe I should offload that to Ross or get back to work.
Back to quantum.
Yeah. And then the Z rotation in the general case becomes this guy, which it's actually quite straightforward, because if you think how these LCUs work, is you start in the 0 state, rotate to some superposition state, do your select, and then rotate back onto the 0 state. So just to perform a reflection on the 0 reflection into the orthogonal space of the 0, 0 place, you just need to reflect around the 0, 0 element, and that's what this is here. And what you see in the literature, which took me forever to figure out, is you see pi used as the projection space. So they like to think about it as a general projection, but in practice, you always typically use 0, 0, 0. Okay, so that's the circuit that they use, and if you can verify that, that will give you a reflection around 0, 0, and generate this Qubitisation. Okay.
Controlled gate.
Yeah, it's a multi-control. Sorry.
Are those implementable?
Not natively. Well, I mean, some ion traps have kind of these iron crystals where you can do global coupling with the phonon nodes, but so in theory yes, but in practice no.
Just have a
Yeah.
signal.
Yeah.
Typically you just do 2 qubit gates.
Yeah.
There have been some linear, there's some linear decompositions of these now that exist. So don't be scared of these multi-controlled. Use our compiler. Yeah. This is what I mean by being more explicit in the orthogonal space, because if you see it, so this is what I showed you before, where pi here is the 0, 0, 0 states, computing notation. But you have to form this reflection, you need to reflect around this guy. But rather than reflecting internally inside the space of this register, which I found very confusing, you can just project onto a qubit, and then you'll naturally have two entangled orthogonal projections. You can do it's quite, so this would be just psi plus 0.0 plus psi plus 0.0 per, where this would be psi 0.0 1, psi 0.0 0. So it's a bit more easy to understand. And this is kind of what you see in all of the QSP literature, this construction, but you can actually do it equivalently this way. But
so because of the amount of data you effectively combine that and still qubit into your other representation.
Yeah. I recommend doing this by hand to figure to prove it to yourself.
Take a phase kick.
I would say not in this case.
So
maybe if you're in the eigenbasis. I haven't thought about it like that. I can't answer your question. I would just prove that it's a negative, gives you an orthogonal space basically with a negative sign.
Mhm.
Okay, shall I move on?
Yep.
Yeah, so this is, so we start saying before, so we've just formed the Chebyshevs of the eigenvalues, which by the matrix polynomial form of acting on the singular values. In a Hermitian case, the singular values are the eigenvalues. We can do the Chebyshevs, but can we do anything useful with it? So this is what the work of this paper was. So they use this idea of Qubitisation to do phase estimation, and they have some very powerful circuit identities which they use to do the LCU, but it's a completely general method. They just throw all this crazy technical stuff and it's kind of buried, but you can just apply this to the simple example that I showed you in that case. So I think it's very instructive to do that. You don't need to go into that paper. I've saved you like a week. Okay, so this is what you do. So W is that reflection operator. This guy. And then when it acts on the eigenbasis, in a very similar way to how phase estimation works, where maybe it was a board, but you could, it's traditional phase estimation, this would be e to the IHT, and then you can get the eigenvalues of when it's acting on the eigenbasis, e to the IET, of whatever eigen.
Transform it together.
Exactly, yeah. But yeah, it's exactly the same idea, but now rather than it being, we have this slightly more convoluted operator, but it still contains the eigenvalues here, so we can use these tricks. And the authors showed that in the asymptotic limit, this is much more efficient. And they did about 5 papers, each one more and more complicated, where they apply they apply double factorization, which is where you do a double SVD on the Coulomb operator, and then you get basically 2 unit rotations and some singular value matrix, and some clever truncations on that. But all of it is the same overall algorithm, which is what I'm going to show you here. It's just they just treat the operator slightly differently, and the complexity reduces. Yeah, it is clear. This is now acting on it. So this is on a perfect eigenstate. So you just have one eigenvalue, and this is acting on a linear combination of things. And this is true because this decomposition is general to whatever rotation you are in the eigenbasis. Okay. Now, phase estimation, quantum phase estimation, I think, is really motivated by the quantum Fourier transform, the inverse quantum Fourier transform, and it's actually very complicated. I think it's one of the most complicated algorithms to derive. It's not actually that trivial, and particularly when it's given us this elementary thing you're meant to derive, but particularly when they start using these fixed point binary representations and mapping into it, it's like completely twisted my brain. Yeah. But yeah, what is fixed point binary? So fixed point binary is basically if you have 3 qubits, your 0, 0 will be 1/8. But your 0, 0 will be 0. Well,
Half.
0, 0, 0 will be 1/8. You're incremented by 1/8, 1 over 2 to the n, basically. Yeah. And that's what this basically means. So if you have, I think, if you had 0, 0, 1, that would be 1/8.
Yeah.
Yeah. Yeah. So that's what this means, is that.
Just for 3 cubes. Yeah, okay.
Yeah. But yeah, so the quantum Fourier transform basically says if you can get into this basis, which is powers of some eigenphase. So how that? Yeah. So yeah.
You keep on doubling as you go up.
Yeah, exactly. And you use phase kickback to generate this exponentiated phase. And as long as you can get into this basis, you can always get out the binary which corresponds
Is
to
that
the.
2 pi meant to be there?
This is from Nielsen Schwang. So
Just because. Oh, yeah, okay. Yeah, okay, yeah, I see it. Yeah, sorry, I was just misreading something, what pi was.
I just have this from the textbook.
Yeah, yeah.
Yeah, so the idea is you get into this powers of phase kickbacks, and then it will then take this. So if you have, I don't know, something with some operator which had a phase of a quarter, or 1/8 for either just, and it was in the eigenbasis which had the eigenvalue of 1/8. As long as you can get it into this construction with phase kickback, it will then map to the 0, 0, 1 thing. Okay. Yeah. But yeah, so this is what I mean. It's like quantum phase estimation is motivated by this. So this is the construction of a phase estimation, is that you have these powers of the operator, and if this is in an eigenphase, you will have eigenbasis, which it always is, but if you're in a single eigenstate, you'll then get phase kicked back onto this onto the registers, and then the Hamied basically get you into the basis that I showed you before. Now, this controlled U in trotterization phase estimation is a exponential powering like product, but we basically take our Qubitisation construction and we do a controlled Qubitisation. Okay, so this is the LCU before. So if we go back to this guy, this is the LCU, and this is the Z. But because if you think about how control Z's work, they're symmetric gates. It's quite subtle. This is the same. You can put the Z here if you wanted, but this is the controlled Qubitisation operator. Okay. And we just apply it in exactly the same way as you would with traditional phase estimation, but we now just have an extra ancilla register, which we have to post select on. And this is a bit misleading, but this will be done at the end of the thing. Okay. So yeah. So this basically gets you this guy. Well, yeah, to some extent, yeah. But yeah, no, yeah. So you can get the eigen. So you can basically use the controlled. You can basically get this exponentiated e to the I cosine e y. And when you post select, you put you into this corner. Probably should have step a bit more. But the idea is that you can get the eigenphase out by using this construction. Okay. Well, I guess has it been an hour already?
Yeah.
Oh, sorry. I can keep going.
No, yeah, I think we booked until 1:40, so.
Okay, so that was the first use case of Qubitisation. Pretty cool. It's a bit of a different way to do phase estimation, but the next step was to take it further and then apply. Like I also go from the Chebyshev polynomials to the generalized with some caveats. But yeah, so we want to do functions of Chebyshev polynomials. We want to do functions of the polynomial approximations of these operators. And this is the circuit construction I'll explain in a second. But you can see it's kind of related to what I showed you before, right? This form. You got this Qubitisation, but instead of just being a Z, you've got now a phase Z.
You can do that because it's those qubit spaces still invariant under that phase Z.
Exactly, yeah. Which it's just acting on the qubits, but it's only acting on in this case it's very explicit because it's only acting on the qubit that defines the Qubitisation. You could do it on this register if you wanted to as well, like in this case, where then you have to be a bit more careful about how you define the Z rotations. I think the diagonal Z would still be fine in this case. But yeah, well, I mean, this is why it's easier to think about like this, because you just have the Qubitisation qubit is quite explicit rather than it being an internal Qubitisation space, which is quite confusing. Okay, so this part is kind of, I want it to be complete and provide the proof. Bit dry, to be honest. So yeah, so how do we then go from? Let's take a step back. Let's go back to a single qubit in the same way as we had before. We have a single qubit. We can then derive, even the single qubit picture. So we don't even have an ancilla space anymore. This is just one qubit. We can still derive what set of polynomials can be achieved through just rotations around this two qubit subspace. So this is what the quantum signal processing theorem is that how much information can we get out of a single qubit, basically. Okay, so what did I put here? I'm going to probably have to figure this out at the same time as you guys. All right, so the first one is what is equivalent to the LCU before this. But this is like it's an analogous to the two qubit subspace, so the Qubitisation subspace, but it's just for one qubit. So
Yeah, so you can replace the phases in the second one on that longer modulated phase by pi of 2.
Exactly, yeah. Yeah, well, and in this case, it's 0, I think.
Or it's,
I was a bit confused by this, yeah.
Debating it's.
Depends on how you do it, the phase convention is used. Yeah.
Yeah.
But yeah, you can kind of see that this is the Qubitisation vector, the rotation that we had before. So just by, if these go to 0, this becomes an identity. Then we just fall back to the exact Chebyshev polynomial that we had before, because the O's are exactly the Chebyshev polynomial. So this is kind of the first intuition of like, what happens if we start to mangle add a bit of extra freedom into the polynomial expansion, into the product of rotations, basically. So I remember before what we were doing. It's just a rotation right around. We're going around. You think about it in this, we're rotating around the sphere, right? What we basically have done is we've gone out of the plane. We're now in the sphere. Okay, so this is our y, just our y, but now we've got our y and our z, and that gives us a bit more flexibility. And that flexibility is what allows us to basically do polynomials rather than just Chebyshev. It's not very intuitive. I'll give you that.
So getting the Chebyshevs seems okay, but for a general polynomial, how do you know which phi's you need?
Yeah, good question. So this is where I actually think that it's a good question. I've got the proof, which is dry, and then I've got the numerical version, which is much more intuitive to me because you just do least squares. What you do is you basically. I'll wait till the end to explain this. It might make more sense. You basically turn this into a cost function and then put this against your function that you want to fit.
Okay.
And then you just minimize it.
So
and it works.
the higher the degree,
Yeah,
the
exactly.
harder it is to.
Well, so yeah. I'll explain this in a sec. All right. So now it's going from same example as before. But now rather than in a single qubit case, we go back to our multi-qubit quantization picture. And it's exactly the same, but rather than doing the z, being e to the I phi z, here we do e to the I phi z pi, and that's that 0, state that this is what they call the projector, is that you're projecting to the 0. Yeah. So it's exactly related to this one. Right, so it's the reflection space. It's a vector that you're reflecting around for the quantization. But rather than just reflecting now, there is the freedom to do other things. Okay. Yeah. But in this case, we're just reflecting as pi over 2. So what this is showing is it's now the Chebyshev polynomials in the Qubitised, in the matrix polynomials picture, where we recover the Chebyshev polynomials by just doing e to the I pi to z pi or z0. So this equation is exactly equivalent to this guy. Yeah. Which is a different way of expressing it. All right. Okay, so this is, I don't know if maybe I can skip this, I don't know, but this is the quantum signal process. So it's obviously not intuitive that these rotations will give you any polynomial. These phi. So this is what the quantum signal processing theorem is that there exists a set of phi's that give you a d minus one approximation, a D approximation polynomial. With these three caveats. So yeah.
What is the, so I guess the first one kind of makes sense because you're applying with D iterates.
Mhm.
And then the last one,
That's the unitary constraint.
okay, and then where does the middle one come?
Yeah, so I'll show you proof by induction.
Um,
Maybe you'll probably understand it better than me. Yeah, so this one's kind of intuitive, I guess. It's not, it actually shows that it's not always D. D, you can actually have cases where you have lower Ds as well. The reflectional case is an example of that. But this is obvious because it's just, this is a unitary matrix. 2 is quite challenging to prove actually. So yeah, so this is the third one. So if e to that phi z is multiplied by O, we know these are both unitary matrices, so that constraint's obviously going to hold there. What actually is that? Is that the norm? It's a determinant, isn't it?
Yeah, it's the determinant, but you can also just view it as taking the, the adjoint, and then when they multiply together, it should be one unitary.
Mm-hmm.
So you'll get the adjoint of U, the iterate itself should give the block, should just give 1, and that's I'll just repair from the definition of what sub psi is.
Yeah. Yeah. So this is
But yes, also the determinant.
yeah. Well, I guess because it's a unitary rotation. Yeah. So yeah, because SU2 will be -1. Whereas this is U2. Yeah. Okay. Yeah.
I think it's worth saying that's a quite strong condition. This one. Like just think about polynomials that do this. 2 pairs of polynomials that can do this. P and Q.
Yeah.
That's quite a. You're basically saying on the interval 0, 1, these two things must be so constrained that they always have this equality. That's quite a strong condition.
You're fixing the end.
Well, these are the split shape ones.
Yeah.
The shape ones, but you come up with an element in this one minus x squared stuff.
Yes.
So now looks like a normalization condition on 1.
Yeah, the angle is on
Angular momentum, which angular momentum?
harmonics.
So it's orbital angular momentum.
Yeah.
Those are normalized on.
Yeah, but those are L to normalize the longer one.
There are equivalent proofs of this with Lagrange polynomials. Lin got a paper on it, I think. They use them in the symmetric quantum technical thing. The way that you prove all that with Lagrange. But I mean, you can always translate between the polynomials. It's not really a problem. Yeah, so there are now, I think there's some ways to get around this constraint now. People have done some clever things. This is one of the areas that obviously is identified as a problem. Right, as you correctly said. Okay, now this proof is quite strict. So this is an inductive proof.
It's reverse induction.
Yeah, reverse induction. I got very confused because they stated at the beginning what they're trying to sell. And I was like, what?
Yeah, I know this is from the.
Yeah, I just copy and pasted it. Yeah,
Took me a while to figure out what the hell was going on.
but maybe you can explain it then. Okay, so
Yeah, it's just a reverse induction. It's not so clear. I mean, it's, I guess, basically you need to show that whenever I have the K case, if I assume K,
Mhm.
then I can prove that K minus 1 is also true,
yeah.
which is of course not how conventional induction may be used. But if you have managed to prove such a situation And in addition, you have managed to prove that I have a infinite sequence where the base case is also true.
Mhm.
Then it necessarily follows
Yeah.
that it's true for all natural numbers. You can just write down what you need to do for induction and use those two facts, and that's too bad.
So here is the base case, right? So the possibility of P equal to phi and Q equal to 0, that's just an RZ rotation, right? So that's P equals to, as D equals 0.
Yeah, so the base, the infinite sequence is this one, when D is even.
Yeah.
So for D equals 0, 2, 4, whatever, you can have this true, which means now I have one infinite sequence where it's always true. And then we're gonna now show that whenever D is true, D plus 1 is true implies D is true. And that will then, that is equivalent to induction.
So they make it easier here by using the pi/2 relation. So you can see that this is now this is infinite, right? But it's still a D equals 0 polynomial.
Yes.
So that's that strange case where the infinite series in the pi/2 case, the expansion will always go to this, which is this polynomial is much lower than whatever D could be. So it's not completely like D mapped to D in the expansion. Yeah.
So there are many phases that can produce the same rotation.
So it's just the reflection really like going back and forth, basically. All right. Now, I don't know if I can follow to explain that.
Yes, so let's see. You can, by assumption of the, because we've assumed that the case for, so we assume we have the conditions now satisfied for some D. Now what we're going to attempt to do is show it for D minus 1. And the reason for doing all of this craziness, you might say, or wonder why, is because now we have these conditions, we can kill the leading coefficients in the D minus 1 case. Because in the D case, there are certain constraints that are holding from the conditions 1 to 3. And that leads us to be able to kill the leading terms. Because remember, we had that the condition 2 was this kind of strange one that said they're even in the parity must be different, they must differ. So just to be clear, parity here means it's either an even function or an odd function. So all right, so when that is the case, you can just imagine there's probably some parity thing you can exploit, right? So that you can kill one of the leading terms, the leading coefficients of P or of Q. These differ by a parity. So one's going to be a power of absolute power of 10, and the one's going to be power of 9. So you can kill one of the terms because of the leading coefficient.
Yeah.
It's just it's a bit involved, but it's not so complicated. But
So you start from the even case from the last slide. And then,
no. So you can start from any D. You can start any D.
Yeah.
D mod 2 is something. It's just that we know that the P and the Q are going to differ on their highest power. It's to L, it's to L minus 1.
Yeah.
And that means that when you have this condition, so we can write this,
gets killed. Yeah.
and now we're going to be able to force
I see.
on strengths.
So this 2 really falls out of 1. In the case where D, you have D and D equals.
D.
If that was an equals, then you can prove this from this, I guess.
Yeah, I'm not 100% sure. I actually had the same question about how independent those connections are. I kind of,
Yeah.
the jury's out to do something. To me, I'm not 100% sure.
The Newton term.
Yeah, it's good. That's actually quite a good point.
Can you explain what this power set is? Material and material minus 2.
So if P has has degree L, then P squared will have degree 2L.
Mhm. Yeah.
Absolute value. So now the same for Q will have degree 2, or have L minus 1, and so squaring it will have 2L minus 2.
Yeah, yeah.
Now, when I take x squared on that, that's going to increase that beta to be on the two.
Yeah, I think I'm pull the x's in, okay.
Right.
Yeah.
So it's, even though it's the L minus 1 term, because of multiplied by square, I can pull it forward.
Very nice. Now, I don't know why they felt the need. I'd like to know the intuition as to why they had to prove this. Like,
Well,
it's like it's not obvious that.
I mean,
The statement is there is a set of phase factors, but here you're just proving polynomial things. It's like it's unclear like when the phase factors come in at this stage. Because it seems that the proof is about finding optimal phase factors.
no, the proof is the QSP proof is saying that in the one direction it says when I have this phase modulated circuit, I can reach certain polynomials.
I see.
It's also saying that this is not just a sufficient, but it's a necessary condition. In other words, anything that looks like this is reachable via that,
So
by
it's-
something like
It's
that.
really the reverse statement, which is the.
So
important one.
that's a powerful, like the powerful one. The sufficiency one is kind of what Qubitisation to some extent is about. It's saying if I just apply this many, many times, I'll get a polynomial. That kind of makes sense because I always have a polynomial each time I multiply. But the powerful statement is the reverse. It's saying anything of this form, there exists something, some phase factors, which will get me there by that kind of function.
But yeah, as you said, the constraints on the polynomial are quite strict.
Well, quite severe. I mean, there you go. You can already see it because it has to be equal to 1 on that point. So it is when polynomials equal constants on an interval, they're just constant. They must be constants, right? Polynomials vary. So on the interval x minus 1, 1, it's all equal to 1.
Mhm.
So they must be the identity. Yeah, this is, yes, I would say so, yes, because by continuity.
Yeah.
Sure. But the difference, not the polynomials. Not P and Q.
Yeah.
No,
The
maybe
identity.
different. Yeah, yeah,
Px squared
yeah.
minus.
All right, we're not finished yet.
Yeah. So then from here, this is how you can choose your phases such that the previous identity
Okay, good.
holds. So we wanted a statement involving the Lth coefficients of P, or the highest coefficient of the P polynomial, and the highest coefficient of the Q polynomial. And we want them, we want to remember our goal is to go to say that the statement, if it's true for D, it should be true for D minus one. So to have that holding, we necessarily need that, especially the second one, to say that I'm switching, they need to move in lockstep from having different parities. That must mean I need to somehow kill the lead. There must be a way to get rid of those coefficients. And we do that with a phase, a well-chosen phase. And the well-chosen phase is the ratio of the leading coefficient.
So that kills these being,
Yeah,
kills the one of the,
the alpha squared minus beta, alpha L minus beta.
is it the P or is it the Q? The Q, surely. The Q that
Um,
gets killed. It's D minus one.
well, it's the relationship between those two. So this, we want this. Okay, well,
Yeah.
that is what the last conclusion was.
We want to kill B after the.
And then if I divide it, sorry, can you just hit?
Oh, yeah, I see, yes. Yeah, I can see you go, because but you can just make beta go to 0 or to 1, right? Is that by taking the ratio? And
Take the ratio. And can you just go to the next slide? Just be clear. Yeah, so at this point, when I do all of this business, which is just adding another, what I started with in the Dth case, now I add another reflection and another step. It now appears that maybe I have increased the degree of P tilde. Okay, but in fact, we can just simply choose a phase, this phase here, so that if it's chosen like this ratio, then the leading terms will cancel. Yeah, are equal to 0, and so that's not the case. And it's actually, where I should actually dig into this and understand this a bit more. This is somewhat clear, but that it also works on Q tilde is quite remarkable. Because for the P case, for the P tilde polynomial, it's got a very nice structure. Somehow the structure works out really nicely. In other words, 7.113 is maybe expected, but that it also, the same phase also works for 1 degree lower, 1 coefficient lower.
Cool.
So
Okay. Very nice.
You can also use this as a way to figure out, I mean, you're talking about least square approximation. You can also use this to calculate what these phases should be by this inductive procedure.
Sorry, I want to slightly.
What is it?
What's the significance of, yes, exactly, what is it that we're trying to achieve with is characterizing Q on P, because we want to apply P.
Okay, so your procedure kind of, global picture kind of looks like this. You sort of like, what I would like a polynomial, I would like a function of some matrix. Let's just do the most simple case. I want the unitary time evolution operator. So I've got my Hamiltonian. I want e to the power of I h t. Okay, so now what I'm going to do is I'm going to try and do one maybe obvious thing to do is a polynomial approximation of that. Now I need to say, okay, I found some polynomial approximation of that. So therefore, I have found some polynomials, and I want to know, is there a circuit of that form that when I do this modulation, I'll actually end up with that polynomial in the top left block. So that when I do this post selection, I'll actually end up fine in that case, let's say it's high resolution. So that's kind of like the global picture. I'm like,
Yeah, no,
this is what you want to start with, this is what you want to end up with.
Q is important because it's a 2x2 Qubitised rotation. So this is a generalized rotation around a Q. And Q needs to be constrained to be, Q has to be constrained to that set to make that a rotation around a sphere.
So the problem here is actually finding so we need to know what Q is obviously to be able to implement the surface. That's-
Yeah, exactly, yeah.
Q is flexible. Do we care too much about what we want to implement P effects? So we can just pick a Q that satisfies it.
This is a good question, so how do you do that? Think about those. Remember how, look at the condition 3. That's a strong condition.
Rearrange that and we get Q.
Yeah, that's
Yeah.
basically what they're.
Okay.
You could select on Q if you wanted to.
A whole interval, 1 minus 1
You can still, it's true everywhere in the intervals.
Well,
So
I want,
yeah, P function. I know P and like,
Yeah, as in if you
rearrange for
have one
Q.
target, then the other one.
but
would be
Q
wrong.
has to satisfy that.
yeah, so I rearrange for Q and then this is my Q that I want.
You might be able to do that.
But that's equivalent.
Yeah.
So,
But then it sort of says that like, if that Q could exist, that this would be true. And that's fine probably as long as P doesn't have a bit of 1. Then you can just pick the corresponding Q.
Does it get harder as the degree gets higher to pick a Q that will satisfy the constraint?
I mean, probably, yeah.
Yeah.
You would expect.
Right?
But so the basis that you're using for QMP is different kinds of activities for numbers, right?
Yeah.
I don't know anything about activities for numbers.
Yeah. No, I don't really either.
you can put them in general.
Yeah, you can do what
Yeah,
say.
as long as it can hold though.
I think they're chosen because, well, they're nice because there's some proof, I don't know, but they converge quite well.
Yeah.
Hibbersheim polynomial is like a nice, they're just well behaved,
Yeah.
they're well behaved.
Well, that depends on the features that you're trying to get.
Yeah, sure.
But
I think it's the legacy thing as well, like the derivations came from Qubitisation, which yes, they did the
Yeah,
cherry
not most of that, definitely,
Yeah.
wasn't these are going to be. Again. Nice, I think, this is what.
How high, because you mentioned you want to approximate the function with a polynomial. So how high a degree have people managed to get to when they implement?
So yeah, good question. So this method is not scale well. So this is the analytical. So remember, you have to have a polynomial approximation already, right? So you've got a NumPy Chebyshevs or whatever.
Mhm.
You have to fit this to that. It's not the actual function.
Yeah.
But yeah, so this doesn't scale too well. But there's the least squared fitting, where essentially I'll come onto that in a second. But that scales to like thousands of phase factors.
Oh, okay.
That's kind of efficient. That's like, it doesn't really have a. Yeah, so I think they've gone to like 10,000.
So you can get a pretty accurate approximation.
Yeah. This is a big question and probably a big problem with QSP and QSVT in general is if you're doing a block encoding sequentially, block encoding is really expensive. And you're doing one phase for each one of those. You need 10,000 phases, and this is not going to work as a method, basically. Yeah. So I think a lot of scope is maybe you can parallelize it somehow. That could be a nice application. Sequential phases, I don't know. Yeah, it's quite a complete recipe, this. It's quite difficult to see how to advance QSP, to be honest. And this was what there's a paper called the grand unification of quantum algorithms. You can approximate all quantum algorithms known through these function approximations. Anyway, I'll move on because I'm getting hungry. Okay, so the last slide is essentially this. What we're trying to do. So now we can do any. So you really have to think about it. This is the rotation. This is a series of gates that you apply. But now we're doing on a block encoded unitary. Okay. So that's a bit confusing, but you can kind of see what's happening if you think about it again in the eigenvector basis, because you're now manipulating the eigenvectors directly with the polynomial that you've implemented, because you have this Qubitisation space. And a polynomial on the singular values of a matrix is a matrix function. Right? Like if you think about it, if you do like SVD, the US, so if it's a symmetric matrix, it would be USU dagger. And then if you do USU dagger, USU dagger, USU dagger, then you can all the matrices cancel and you get the power of the yeah. So this is again why you really have to think about it in this eigenvector basis. It's the and this is actually a bit misleading, I apologize. So this circuit would not be this. This circuit would be 0, 0, 0, K 0, and then 0, 0, 0, K 1. But yeah, that's what this guy is. Sorry about that. So this is the circuit. The important thing here is that the block encoding, like how do you get the matrix into the circuit to do the polynomial transformations on it? This is where, so in the complexity results, it's all about the structure of the circuit, like the actual time of the circuit. But the prefactor of the implementation is all about this guy. So there's like, if you can improve the block encodings, then you can really reduce the actual numerics of the circuit. And that to me is what is more important than the complexity results.
So like the final success probability that you get at the end will depend on the initial success probability of the block encoding.
Yeah. And I don't know, and there'll be some factor here as well, I guess. Yes.
So is there any question to see how the block encodings might affect that probability?
So the success probability is only down to the operator. You can, so like for example, if you think about looking at the Coulomb operator, I don't know if you're a chemist, you know, yeah. But so if chemists have this operator, it's like it's the rank 4 tensor, contains all the electronic interactions. You can manipulate that with like SVDs and things and express it in the same operator, just SVD did. That actually has a much simpler block encoding, but the success probability is the same. So like the success probability is purely down to the operator. So there's loads of tricks from the chemistry perspective that are quite useful. There's like how do you truncate the operator, like density fitting, things like that. They use all those techniques to kind of remove the complexity in the operator. All right, last slide. So yeah, so you got that nice analytical relation, but this is much more intuitive to me because it's quite nice to implement. So how you do this is you take the single qubit. So this is used phi. This is a polynomial function that you want to fit. So I don't know, these you can the numpy, the scipy functions are very good here. You got some polynomial you want to fit, but then you don't know what, and you need to obviously assume that you can actually fit it with the constraints before. But yeah, what is this cost function? So this u phi, you need to build u phi. What is u phi? The u phi is this guy. So it's just a series of, it's just a 2x2, the 2x2 matrix product. So the cost function is this, where you then post select into this block here. Well, it's not quite that one, but yeah, the equivalent 2x2 matrix, you just post select into this one. So you can just do it in numpy as like a series of 2x2 matrix products. And then you pick the 0, 0 element. And then you do least squares fitting against the polynomial approximation that you want. And then you can do like 10,000 things. Yeah, and there's been a few generalizations of this to Fourier. So rather than block encoding this, you block encode the time evolution operator, which is e to the I ht. So if you think about, then you're not block encoding the operator a, which is inside here. You're block encoding the exponential of that. So it's like naturally is that your signal processing the Fourier expansion there. So it's kind of quite natural. Interesting. as a Fourier quantum signal processing extension of it. Yeah, that's the end of my talk. So, yeah. Any questions online? All right, cool. Thanks, Ivor.
Can you stop recording?
You explained it to me. I was trying to figure it out in like 10 minutes.
Thank you very much.
And then everything is,
Yeah.
what the hell is this stuff?
I was like, this can't be too difficult.
Do you remember how we stopped recording?
Fuck.
Oh, yeah.
Yeah.
That should be.
But I don't think there's a numerical